Okay, so let's start off on our lab session about modeling count data, and I'll just go through and remind you what the sort of the assignment was here for our hands-on problem 4 and what we're going to be doing. So recall here I talk a bit about our phase 1 dose finding study, and there were various things that various pieces of information collected, but one in particular was one of the adverse events, which was the number of coughing events that were measured. Actually, let's bring this up to full size here. There we go. So we're looking at the total number of coughing events over the duration of the trial, and it was a 24-week trial. And we're going to be looking at some different possible event count models to try and describe that, so that one, you get practice looking at some different possible models, and two, we can also sort of look at the look at a model selection process while we're at it. So again, it's a reminder here, it's a phase 2 dose finding trial. It was parallel design, 100 patients per arm, with different dose levels of MI2. So we've got 4 treatment arms, placebo 20, 40, and 60 milligrams per day, given over 24 weeks. And we're going to be looking again at the total number of coughs. So here is a construct a model for the count of coughing events as a function of dose, and we've got our data. We'll take a look at that in a minute in the data set itself, but just remind you some graphical looks at the data. Maybe actually start with the right-hand side here. Here I've plotted the mean count of coughing events, just taking the mean over the various patients, and you can see here it's going up from a mean of about 1.5 for the placebo group up to not quite 3 here for the 60 milligram group, and it appears to be going up in an approximately linear fashion as the dose goes up. The left-hand side is a visualization of how those counts are distributed across the patients. So on the y-axis we have number of patients, and on the x-axis it's the number of coughing events in there. So those are shown as a histogram here to describe this distribution. So you can see, for example, down here with the placebo group in the lowest panel, you've got looks like roughly 50 patients had no coughing events. Then you've got 20 patients had 1 coughing event. Looks like somewhere around 8 or so had 2 coughing events, and so on. And you can make that same kind of inference as you go up. And in general, it's shifting a bit to the right as we go up in dose. And then overlaid on that was a picture of a Poisson distribution that has the same mean count as the this collection of patients. I've also overlaid the mean, you can see up here, and what you see is this Poisson distribution seems at least the mode is shifted to the right compared to the observed data. So it looks like a regular Poisson model isn't going to quite fit it, and that then gets further emphasized by looking at the sample variances of the observed data, which, if we look here, in all cases is greater than the mean, whereas for a Poisson model, recall that the variance and the mean should be equal. Okay, so we got some clues that a plain Poisson model isn't going to be our best choice here, but we're actually going to start there as sort of a baseline, and we'll work from there. So the first model we're actually going to look at is going to be just a plain Poisson model with where the event rate depends upon dose. So you can see I've written this out as the number of coughs is distributed Poisson with the parameter equal to the product of this lambda I times ti, is where lambda I, so while ti is going to be the duration over which the coughing events were observed, and the lambda I then is going to be essentially the event rate. It's going to be the count per time unit in here. And now it turns out the data set we've got that I gave you is kind of ideal in the sense you'll see that all the patients had the same duration of observation. In reality, of course, in most studies, you do have a certain fraction of patients dropping out, so the duration over which the measurements are taken are going to vary somewhat across the population. So I've included that in here as a way to illustrate how you can account for that difference in duration. And then that event rate then is modeled again as a straight line. And then we're just going to go ahead and put some very weakly informative priors in here for our intercept and our slope on that. The only, I guess, this one informative bit that you see in there is I have enforced non-negativity on both A and B here by using a log-normal rather than a normal distribution. And that makes sense because we do want to restrict lambda itself to be non-negative in the Poisson distribution. Okay, so let's start by implementing that. First, again, let's take a quick look at the data in its form as it sits on the file. Where'd it go here? Yeah, here we go. Our ME2 cough count data.csv. Actually, did I call it cough count or cough time? What did I tell you it was? Cough count. Okay. So let me fire that up quickly just to take a peek. Since that's what we're going to read into our R script. Come on, Excel, open up. Okay, so just quick visualization here. So here you've got a patient identifier, dose, our count, our cough count here, and the time over which the measurements were taken. As I say, these are actually all 24 in this artificial data set for this case, but we'll go ahead and use it as I showed in here. The patient identifier we really don't need in this particular case because we're only going to have one observation per patient. So we're not going to be using a mixed effects in the sense that we would normally do if it was longitudinal data. So we're basically just going to use dose, cough count, and time in our modeling. So let's go ahead and build a model. Actually, first let me bring up the R script that we're going to use. You can see, and this is also in the materials I gave you, you should have something in there. You should have your directory called hands-on4, and there should be something called hands-on4 Poisson.r. Open that guy up. Come on. Oh, that's not where I wanted to open it up. Excuse me. Let's do that again. Actually, let's just do it this way. Okay, and make it a little bigger. This one you'll see I did something slightly different in terms of how I handled the naming inside of specifying the paths. I have a model name which I called hands-on4 Poisson, but then I also have something called the example dir, the example directory. So the distinction there, as you can see, the model files are all going to start with the root hands-on4 Poisson, but they're contained inside this example directory called hands-on4, and we'll use that throughout the examples for our hands-on4 example, and that gets taken. The rest of it just gets taken care of in our boilerplate down here for specifying the various paths. Okay, let's see. Let's go on down. Just point out a couple of things. We've got our data is being read in here. Nothing particularly new there. The plots I was showing you on the let me go back to those. The plots right here are actually created inside that particular R script. So if you go down here, you'll find that first chart on the left is taken care of by this rather lengthy bar chart example here. So if you want to see what the tricks were to get the various components into that, this illustrates that using the lattice graphics approach. And then that other plot that's just showing the mean counts versus dose with the error bars in it is this next collection right here. Okay, the data management is trivial in this case, so you can see it right here. I specify, I use the name N patients, you can call it that, or N observations, whatever you want to call it. In this case, the number of observations and number of patients is the same, and it corresponds to the number of rows in our data set. I'm going to call the duration of this, or the end of the measurement interval, I called it T end, and that just comes from our time column from our data set, and dose is the dose column, and then N cough is that cough count. So that's the naming convention I'm going to use in the R script that we're going to write, or I'm sorry, the WinBUGS model script that we're going to write. And then you can see there's some initial estimates being provided for our slope and intercept, or in particular the logs of those. And that one, that one I can probably sort of see how I did the eyeballing on that, because recall that if we go back to the plot here, I can look at this and say, okay, well, at dose equal to 0, it looks like the mean count's roughly 1.5. Okay, and recall that in our model, the mean count would be the product of the lambda and the duration of observation. So the actual lambda in our model would just be this 1.5 divided by 24, our duration. So if we go back to our R script, that's just eyeballing it, and thus that's why I have this log of 1.5 over 24. The half in here for the standard deviation is just a crude way of saying, oh, let's just use approximately 50% coefficient of variation on our sampling here to try and get something that we think is a bit over dispersed compared to what we think we know already by looking at the data. And then this other one you can see here where I've got this 2.88 actually comes from the value up here at the 60. Actually, is it the 60? Let me double check that. Make sure I know what I'm talking about here. Okay, come on, there we come back. Yeah, okay, so there I took the 2.88 was just the observed mean then at the 60 milligram dose minus the 1.5 for the baseline here, or for our intercept. Take that difference and divide it by 24, and that gives me a crude estimate of the slope. Actually, that's not, sorry, that's I divide by 24 to get the units right for lambda, and then finally divide by 60 to get our crude estimate of a slope. So that's where the initial estimates are coming from here, just very sort of a very crude eyeball regression, if you like. And then we're going to want to collect our A and our B, or our intercept and slope, for our parameters. And let's go ahead and get we're going to grab our lambda values and our posterior predictions for number of coughs in here. So, and let's go ahead and actually make a model, though, that we can actually work with. Let's make a new page here. Actually, I do want an R. Okay. Again, I want to make that bigger. Okay, so as usual, it's going to go inside of a model block. Now, in this case, we only need one loop because we've only got one observation per individual. So it's just going to be for, I in 1 to n patients. Excuse me, I'm fiddling with something off screen here for a second. Where did it go? Okay, there it is. Okay, and the basic likelihood then is just going to be our nCof. So that's our observed values, our data. And that's going to be distributed. So we need a tilde. Poisson, which is just DPOIS for our Poisson distribution. And that just takes one parameter, which is going to be the product of the our lambda parameter and the duration, and I'm just going to call that lambdat in here. That's going to be specific to the individual. And then we need to define that. And of course, that thing's going to be the product of our lambda, which is going to be individual specific. Oops, I missed something. Need to put in our left-hand arrow here. Times our duration, which we called, what did I call it? T-end. Okay. And then our lambda, we're defining, find you here, we're going to define that then as our straight line using the parameter names A and B. Oops. So that's going to be A plus B times, I think I called it dose, lowercase, didn't I? Okay. That's kind of the core of the model then. In fact, that's everything that's going to fall inside the loop. Everything else is just providing priors on these, and remind myself what those were going to be. So I had log, well, both of them I was using for the logs of A and B, just a fairly flat normal. So we'll just go ahead and do that. So log A is just going to be normal, dnorm, 0, 1.0 e minus 6. I'm going to be lazy. Do a little cut and paste. And oops. B, and then convert those guys to A and B here. So it's just going to be log A is going to be log A, and ditto for B. It's too bad they won't let you put that log A in parentheses on the left-hand side of a distribution statement, but it won't. And I think that's all the pieces. Yeah, I think that's basically our whole model. The only thing that we're missing in here is our posterior prediction, which we could, again, like in most cases, we could either do it here, or since we're passing the lambda values back to the R script, we could actually just generate them by using the R Poisson, or what RPOIS function in R, either way. But we'll go ahead and do it inside here. So call it nCof pred I, and that's actually just going to look just like what we have up here. In fact, I could have just copied this one and stuck a pred on it. Okay. And that's our whole model then for doing a Poisson fit to this data, where where our mean count is a linear function of dose. So we can go ahead and run that. Let's go back to the R script. Come on, there we go. The run I did, I just did sort of my initial sort of defaults here, where I've got 3 chains, 10,000 per chain. In the case of the Poisson model, it doesn't need all that many burn-ins. In fact, even 1,000 is probably overkill, but it doesn't hurt. So I'll just do 1,000 here, thinned it by 5, and go ahead and run it. So we can go ahead and run that. So we've got still time to look at some of these other model variations. I'm not actually going to take the time to run it in real time. Let's actually take a look. Take a look at the results of that I got before. And that's inside here. Give you some idea what the fitting characteristics look like. Okay, well, we only have 3 things to look at in our history plots here. So as usual, we get the deviance and then our intercept and slope here. Things are fairly decent looking fuzzy caterpillars here, so we're fairly clean on that. If we take a look at the our model parameter summaries here, let me bring that up. What the heck? Oh, I was going for the wrong thing. That was my problem. Poisson, yeah. Okay, let's make that bigger. Okay, the other diagnostic, our effective N, you can see is reasonably large. What did we actually have? I suppose, let's see, we did 1,000 for each. We took off we did 10,000. So we got 9,000 post burn in. So out of there, and I kept every. Well, actually, we'll do that. That's what, 27,000. I kept every fifth. What is that? 5,400, I think, is what we end up in the end. So so you can see there's some autocorrelation, but it's not too awful. And we certainly have enough there to make reasonable inferences unless we're going way out into the tails. So that's looking pretty good. So no apparent problems from the convergence standpoint. If we look at the Gelman-Rubin-Brooks plot, we basically get the same answer there. If you want, you can take a peek at here are marginal posteriors, and so you can get some idea of the values. You can see that here, going from roughly 0.05 to 0.08 for our intercept, on the order of 0.0004 to around 0.001314, something like that. For our slope, again, we can look at those values here too. You can see the values we're getting for the various components. I don't know. I don't have a whole lot to say about those other than they appear to be reasonably precise in many ways. Let's actually march on down to the fits. So here we've got our posterior predictions in the form of posterior medians and a 90% credible interval about it, overplotted on our data, and for our mean number of coughing events, and that looks pretty good. But this is what it looks like for the variance of the number of coughing events, and this is actually a pretty good illustration of a posterior predictive check telling you something about your model that you might not be too happy about. So it's a case where there's a clear indication we should reject this model because it's unable to appropriately characterize the variation in our counts in here, since it's pretty severely underestimating the counts. You can see it even puts out a 90% predictive, prediction interval here that completely misses any of the observations. You get, a more, essentially an additional emphasis when we look at it in a slightly different way. Again, here we're looking at number of patients on the y-axis versus number of coughing events. So what you're visualizing here is the black dots, or the empirical distribution of our coughing events overlaid by the model predicted distribution. And again, we've got some problems in here. For whatever reason, the 40 doesn't look too off, although there is some systematic stuff going on. But it's, clearly, for instance, here with the placebo, there's this big zero, high count at 0, which is completely missed. We're again missing the early ones at the 20, and ditto again for the 60. So there are some indications of problems also when we look at it that way. So we've got, it went ahead, it fit the data, it seems to describe the means pretty well, but that's about all. If you were to simulate with that particular model, you would definitely not get a distribution of outcomes consistent with the distribution we see in real data. So what can we do about that? And that's where we get into our models for an over-dispersed case. And our first candidate that I gave you is using the negative binomial model. Okay, do that again. There we go. Okay, so this is a negative binomial model, which can also be described as a Poisson Gamma mixture model. And that's using the Poisson Gamma statement is just saying that that's the equivalent. And we're going to pick a particular Poisson Gamma mixture where the standard deviation of our cough frequency is proportional to the mean in here. So it's going to be our first statement, and our likelihood is going to be just like it was for our Poisson model. The big difference is this lambda is now going to be randomly distributed. We're using a gamma distribution, and it's a particular gamma distribution here. So we've got our two parameters of the gamma distribution, one in which is going to be fixed for all individuals, and the other which is going to vary across them depending upon the dose, and it's going to be related to our mean count according to the relationship you see here. I've got beta I equals alpha over lambda I hat, so lambda I hat is going to be the mean event count. And that again is, we're going to use the same old linear model as a function of dose to describe that. And this just points out again, as I pointed out before, that I parameterize it in such a way where our expected number of coughs is going to be lambda I hat Ti. So lambda I hat now plays a role similar to what lambda I did in the previous model. Excuse me. And it's structured in such a way then that the variance, actually, did I write this correctly? This is proportional to the mean. Actually, I should never try and think through a sentence I'm talking about at the same time as I'm showing it here. I need to double check and make sure that's not supposed to be an SD here. Let's see. I think it is. I'll actually have to get back to you on that. I won't try to figure that out during the session here. I think I've actually miswritten this because I actually think it's the standard deviation is lambda I t over alpha, but let's see. So it's either that's true or this statement is not true about the standard deviation being proportional to the mean. I'll get back to you on that rather than take up a bunch of time trying to make sure I got it right. But by the way, when I figure that out, what I'll be doing is using the fact that for the gamma distribution, if I remember correctly, the variance is alpha over beta squared. So it's the first parameter over the second parameter squared, and so I will be plugging through that to check what the actual variance and the standard deviation come out to. Actually, maybe we actually can do it. Let's see if we do alpha over beta I squared, we're going to actually end up with what? We're going to end up with lambda I squared over alpha. Is that right? So I'm going to get 1 over that's going to be lambda I squared over alpha squared. So I'm going to have an alpha. One of them is going to cancel. Yeah, you know what? I think the problem is I think I forgot a squared term here. I'll double check that, but I think that's the problem, in which case this statement still holds. Okay, in the meantime, let's go ahead and implement it. And let me show you how to do that in Bugs. Let's see, do I have that handy? No, I don't. Actually, just so that we can actually finish all four, maybe I'll cheat and actually just bring that one up rather than type it out in real time here. So let's go ahead and grab that. So the R script looks essentially identical, except I think I left out the, actually let's go ahead and bring it up just in case. I think almost everything's identical except for things like initial estimates. Okay, gamma, here we go. Oops, wrong key. Yeah, Poisson Gamma. So obviously the name changes up here. And the main thing here is, yeah, we're going to have the additional parameter here. Our log alpha term here is added. Okay, you know, and of course it gets added to the list of parameters we want to make plots of and so on. Okay, so that's about the only thing that changes there. So let's go ahead and grab the model itself, the Bugs version of the model. Let's see, there it is. Okay, so what it really I've done here is, if you think about it, there isn't a lot of difference between this and what we did before. So we've got the first couple of statements the same. Of course, we've got our loop over our patients. The main likelihood here is just that the number of costs is Poisson distributed with some mean here, lambda t. Lambda t, again, is just lambda times tn, so that's the same. Where the difference comes in is right here. I've got now lambda is a gamma distributed random variable with our parameters alpha and beta I. And then I've got my definition for beta I. Again, that's alpha over lambda hat. And the lambda hat then is essentially the same statement we had before in the case of the simple Poisson, except that it's now lambda hat instead of lambda. So that's the same. For our slope and our intercept, the priors are the same, but then we have the addition of the alpha, which again I've used a fairly flat prior, but restricting it to non-negative values by using a Lognormal. And then what else? I guess the only other piece I didn't mention is we have our posterior predictions here, my ncof pred. So it's actually a fairly simple set of additions then to implement our over dispersion model using our negative binomial in this case. And so we're going to run with that. Let me show you what the results are here. Let's see. Okay, let's go ahead and bring up the plots. Okay, why is it not making it bigger? There we go. Okay, for the most part, history plots look pretty good, except there's one odd little hiccup in it. Notice for both B and A, there's something a little funny right about here, where one of the chains kind of wanders off in here. If I was going to do a production run on this, I'd probably sort of revisit that and maybe run this for a longer number of iterations to see if if there's a chance that that's off visiting an important part of the posterior that isn't being adequately sampled or something like that. My guess is that's not the case, but I can't tell by looking at this. So I'd probably want to go ahead and run it for, instead of the 10,000 iterations, maybe run it for 100,000 and revisit it to make sure that there isn't something funny going on I'm missing here. If we look at the Gelman-Rubin-Brooks plots, you can see that where those hiccups occur in the middle of the range, you see sort of a hiccup occurring here in our A and B here at the same point. So you get that little bump in there. So it raises an issue that needs to be resolved if you were actually doing a production run. You get all your posterior marginals here. Here we've got our fits to the mean data, so we're looking at the mean number of coughing events versus dose. Let's see, I got a question here from Corey. What do we got? Okay, so the question is, let's see, for prior information, yes, I use this flat normal. Could we also use other distribution as priors, such as a D gamma? And I guess the question I'm wondering, for which parameters are you imagining using it? And whether or not a D gamma with small parameter values is uninformative depends a bit on the parameters. So you'd have to look at the particular case. A D gamma with low parameter values has sort of an odd sort of shape to it, although it's probably not that much odder than using a log normal, I suppose. So the short answer is maybe. One of the things that in general I would recommend, rather than trying to prescribe a specific set of weakly informative priors, is actually consider doing a sensitivity analysis where you actually explore alternative ones. So if your intention is for the priors to have minimal influence on your inferences, I would try a few of them that you think are weakly informative and see if your inferences remain robust to those choices. Says, how did I decide to model lambda using a gamma distribution or any other distribution? Well, the gamma actually comes a bit from history. The negative binomial has widely been used as a model to describe an over-disperse a case where you have over-dispersed counts. So there's actually a very large literature if you look on use of the negative binomial. So it really it was more based upon that convention than anything else in this particular case. As your question implies, there are certainly other choices, and in fact the third model we'll look at uses another choice, though it has some characteristics somewhat similar to using a gamma. The other aspect of this is, of course, I would want to use a distribution which only allows non-negative values. So, natural choices tend to be things like gamma, log normal, but alternatively you could take another distribution and simply truncate it. Something like a truncated normal. It would be, I suppose, another option you could consider. Okay, anyway, let's so just pointing out here what our posterior prediction in terms of the mean count of coughing events, and again things look good, but then so did the Poisson. Where there's a marked difference from the standard Poisson is this plot, where I'm looking now at the variance for our counts on coughs here versus dose. Recall that when we looked at that for the in fact, let me go ahead and pull it up. This is what we saw with the standard Poisson. Now with the our negative binomial model, we can see we do a much better job of picking up the overall magnitude. Now, is there there's maybe a hint of something systematic here. Whether that's something of concern or not, I suppose you could explore other models to see if it makes a difference. We do see here that though there's maybe a hint of something, it's still everything's within this 90% prediction interval. So one way or the other, we certainly have a marked improvement compared to the standard Poisson. And similarly, when we look at our the predictions this way, where we're looking at both our predicted distributions and the observed distribution of coughing events, we can see that things are markedly improved from what we saw. Bring that back up here, where here we're doing things like badly missing the zeros over here and really not capturing the shapes. Here we've done a much better job of capturing the relationship. So again, it's pretty clear just from visual inspection that we've done much better here. Now, other ways of looking at this, if we want to get some numeric comparisons on these two models, other things we can look at, let me show you, would be things like we can look at the deviance, for instance, the mean deviance. And looking at a mean deviance is similar to comparing the objective function in NONMEM. In fact, they're essentially equivalent ideas. They're both representations of -2 times the log of the likelihood. And so to some degree you can compare those, though there's some risk in a trivial comparison, because we're also talking about differences in model complexity here. So you've all seen different strategies to try and go after adjusting for that complexity, whether it be things like the likelihood ratio tests that are often used in the context of maximum likelihood, or using information criteria like a Kike's, Schwartz, Bayesian, or in the case that we'll look at here, we'll use the deviance information criteria. Excuse me. And there's a couple ways you can get that deviance information criteria. One way is if you retain the log file that's produced by WinBUGS. You can see it there. And just remind you, let's go back to our R script here. Now, if you have where we do this call to bugs, if you have clear WD equals true, which I think is the default I had set up in your scripts, if you do that, it's going to delete the log file in there. So if you actually want to retain it so you can see some of the values are in there, put a false right here when you run it. And if you do that, you'll get back, well, you'll keep a bunch of files. You'll have these coda files, the data files, the initial estimate files, as well as the log files in two formats. For our purposes, since we don't, the log ODC is the format sort of native to WinBUGS, and you have to use the WinBUGS viewer to see it. Log.text is just the text element. So if you want to see the plots, you have to use log ODC, but we don't. I just want to look at the text anyway, so I'm just looking at numbers. So let me pull that over and look at it. Okay, so you get all the junk that WinBUGS spits out in its log file except for the plots. Let's go to the bottom, and assuming WinBUGS was able to calculate the DIC, or the deviance information criteria, it will show here. By the way, this is a consequence of the default for R to WinBUGS is to attempt to get it to produce this value. So it's got some gibberish here, but the elements here, and let's see, because I'm looking at it in text, it messes up the columns of what was a table originally. But you've got the first in here, so you can either, when you've only got one dependent variable, which we do, ncof, the two rows here, the ncof and total, are the same. D bar is the mean deviance. D hat is the deviance at the value. It's that calculates the deviance when the parameters equal their means frankly, I never bother. I don't use that column for anything. This value here corresponds to this PD, which is it's sort of like a virtual number of parameters in the model, which actually grows pretty big when we incorporate this mixture model component in there with the gamma. And then finally you have the DIC. And what you're looking for is you're taking the mean deviance, you're adjusting it for the apparent number of parameters, so you're sort of penalizing it for that to get this. So this number here is actually the sum of the D bar and the PD value in here. And that's what you compare. And the smaller that is, the better in terms of what we're doing. Now the one I'm looking at here, I think, which one did I pull that out of? I think I pulled that out of, see, 1200. I think that's the, yeah, that's the Poisson Gamma. So let's do the same. Let's pull the one out for the plain Poisson. And pull that in here. Actually, let me make them side by side here. Let's. Oh, why did you do that? Okay, so if we look at them side by side here, whoops. You can see here, if we just look at the DIC here for the plain Poisson, it was about 1924, whereas it's around 1400. 1399 here for the Poisson Gamma. So clearly the Poisson Gamma results in a much smaller DIC, so that would be a rational basis for choice. In this case, we could have actually made that choice just by looking at the mean deviance itself. You can see here it's 1921 over here. And it's dropped by just a humongous amount to 1200. So unless you had a really extraordinarily complex model that you were going to, that would pretty well tell the story. But if you really wanted to adjust for complexity, you can look at that 1924 versus 1399, and clearly the Poisson Gamma is better. So that's another way of doing the model comparison. Now, also I'll point out, let's see here, there's another place where you can get this information, which turns out to be useful when we actually do the discrete mixture model for the zip. That's a case where BUGS fails to produce a DIC, but R2WinBUGS also calculates it. And let me show you where that is, since it will come in handy perhaps in the future. Let's actually grab one of these here. Let's go ahead and take our Poisson Gamma R script here, and we're just going to run part of it. We're not going to run the whole fit. Actually, I need to, do we have an R window open? No. Okay. There, let's make that bigger too. Okay, let's just run the first part of this. Oops, not that far. Just run it down to before we run the bugs. Okay. Let's see, I got a question here. How much drop of D bar is significant? Is it close to a chi-square distribution? I think I'll bet once we start realizing that we're working with that our minus 2 times the log likelihood is now a posterior distribution, not just a point estimate. I think all bets are off are in terms of a simple sampling distribution. So I would really hesitate to suggest that it is chi-squared distribution. So also once we start talking about significance in those terms, I guess I'm feeling like we're getting into the apples and oranges of combining a frequentist and a Bayesian formalism here that could be problematic. So, I mean, I suppose you could use something like a posterior mean deviance, and you'd probably get answers similar. Well, if you're not using informative priors, you'd probably get an answer similar to what you would if you were working in a frequentist context, or in a maximum likelihood context for doing a something like a likelihood ratio test. But in the once you start putting in priors in here, that's that distributional approximation is probably going to fall apart. The deviance information criteria is intended to be sort of the alternative technique, where you simply compare the numerical values of those, and the penalty that's based upon the estimated number of parameters is the device that allows you to compare two models in those terms. Okay, let me see. I was going to go one step further here, and just remind you. Notice I've in almost all the scripts I've given you, there's this one line that's commented out that's under the save model statement. That if you just run that line, uncomment it and run it, that will reconstitute if you've run the model before, that would sort of reconstitute the WinBUGS results inside R. So what it does is I've previously saved this bugs fit object to a file using the save model statement. This load statement's going to pull that bugs fit information back up without rerunning the entire model. Anyway, let me run that. So it'll take a second here. Okay, there we go. So I've got it, and let's actually take a look at the components of bugs fit. Okay, there's a lot of bits and pieces here, but in particular what I wanted to point out is these guys right here. And that's assuming that you've accepted the defaults I have set up here. R2WinBUGS will attempt to calculate this PD term, our estimated number of parameters, and the DIC values, so you can actually get at those. So I can, for instance, do bugs.fit $DIC, and that gives me my estimate of DIC. That's been returned by the R2WinBUGS. So that's another way. If you don't have the log files, if you can get to your bugs fit object, you can go ahead and grab your DIC, the PD. Inside this mean object here actually has all the posterior means in there, and in particular I can get at the mean for the deviance. So I can do, let's see, bugs.fit $mean $deviance. Okay, and that gives me my mean deviance. So what you're getting is information very much like, which one did I keep? Yeah. So you can see you actually got some of the same values, the 12.2 or 1201.21. Well, that's right there. My DIC, you can see, matches up to what's also in here from WinBUGS. If you really want the PD, you can get that. In there too, so that's at 197.563. So you can get at it either way. And again, usually R2WinBUGS will still make an attempt at calculating the DIC in instances where WinBUGS may fail to do so. Okay, so again, we're comparing that, and we saw that the DIC was much smaller for our negative binomial model. Let's go another step further. Let's go back in here. Oh, actually, let's go back to here first. So we've got those two models, and we've got a clear winner if we compare those. So there was a third case that I suggested, which was another alternative for dealing with the overdispersion, and that was this Poisson Lognormal mixture model. So it's a similar notion to what we did with the Poisson Gamma, or the negative binomial model. So we've got our nCof again as Poisson, but where our lambda is now a random variable, and in this case it's a random variable with a log-normal distribution, or equivalently where the log of lambda is normally distributed with some parameters. So it's going to be our usual variance parameter here. Again, we've got our lambda I hat is going to be our straight line function of dose. We've got again our slope and our intercept, and then our additional parameter is going to be the standard deviation for this particular for this normal distribution here. And in this case I used a uniform that goes over a fairly wide range. Okay, so that has much the same flavor as the Poisson Gamma. It doesn't have that sort of long history that the negative binomial model has, but the flavor of it is much the same. The implementation is also much the same in WinBUGS. Let's go ahead and pull that. Let's see, let's get the right one up. So I've got that right here. Go ahead and, oops, that's not what I wanted to do. Oh, actually, as I was going by, I noticed, by the way, I did, for those who might be interested, I also provided NONMEM scripts for implementing essentially the same models in here. So you'll see a hands-on Poisson.ctl and a hands-on Poisson Gamma.ctl and so on. So those are available if you'd like to take a look at those. Okay, where do we go? Where's that? There it is. Poisson Lognormal text. Okay, again, it's going to look very much like what we saw before. We've got our Poisson distribution, multiplying our lambda by the duration. Here that we've got some transformations going on because of the use of the log normal and having a log transformation. But you can see here I've got the log lambda is normally distributed, so that's our normally distributed value for log lambda, and this is just pulling the lambda out. So lambda I now is a log normally distributed random variable, and here the way I ended up writing this is just to save myself an extra step, is instead of writing lambda hat equals a plus b times dose, I wrote the log of lambda hat is the log of a plus b times dose, but it's the equivalent idea. And then again down here in the priors, the only thing new is our standard deviation here, and then converting it to our WinBUGS convention of using precision instead of variance for our normal distribution here. And we run that one, and let me pull up the results for that. Where am I going here? I'm doing this the hard way. Okay, and our history plots look pretty clean. Ditto in the Gelman-Rubin-Brooks plots. And let's go ahead right to the fit. Fit looks very similar to what we saw with the negative binomial, and also pretty similar to what we saw. Oops, I'm looking at the wrong set of plots here somehow. There we go. Sorry. There we go. I pushed the wrong thing. Here we go. Okay, so that's the mean, and we end up with somewhat similar on the variance in this case. In fact, on first glance, it actually looks like it might even be a little bit better in terms of predicting the some of these terms in here. So, they are very similar results. Maybe even hints of some improvement with the log normal, though the shapes of those distributions, the gamma and the log normal, are not grossly different. The main places they differ is near the lower end of values. And again, it looks pretty clean here in terms of the distribution of coughing events. So at least in terms of graphics, there isn't a lot to distinguish them, and if anything, maybe even a slight improvement with the log normal in this instance. So anyway, tough call to make between those two. If we look at the let's see, we're going to go grab the log file here, and I got to get that back up. There we go. Okay, and let me pull up I got to get the right log file for the other one here, Poisson Gamma. Which one? It should be the one marked. Oh, maybe I already closed it. No, I think that's it. Is that it? Yeah, that has to be it. Let me actually move one of these over. Okay. Okay, so let's see. So the right hand, which one's which here? So yeah, the right hand side is the Poisson log normal. The left hand side is our negative binomial, and you can see there is a little bit of difference in the mean deviance. It's a bit lower for the negative binomial, and in the end, when we penalize for parameters, it remains somewhat lower. So you can see it's 1399 versus 1434. Those aren't humongous differences, and compared to what we saw as the big jump from the Poisson, but it's probably enough, given that what is largely a toss-up between the two, that I'd probably still run with the Poisson Gamma. Let's see, what do we got here? Let's see, trying to make sure I understand the gist of your question, Carrie. So you got what modeling strategy for this type of data are these three models, Poisson, Poisson Gamma, Poisson log normal, popular and should be tested, and select the best one from DIC, diagnostic plot, any other potential model. Well, actually, we'll be talking about another potential model that we'll talk about. The Poisson and the Poisson Gamma, or what will usually be termed in the literature negative binomial, are very commonly used in the literature. The Poisson's kind of the initial default, and the negative binomial is perhaps the most common model used to account for overdispersion out there. The log normal is less so. That was probably, my use of that was probably a more natural outgrowth of the kinds of things we often encounter when we've been working in a mixed effects modeling context, where where we might be modeling inter-individual variation, and so the natural choice in this case would have been to use the log normal for the lambda parameter in here, but in the statistical literature it would be much less commonly encountered. The other one that's fairly commonly encountered is going to be the zero inflated Poisson model, and that's the next one on our list here, which I guess given the time I'm actually going to put that off and talk about it at the beginning of our lecture session on Monday. But that's the other category of model that's fairly commonly used to deal with actually a somewhat different class of of over dispersion, because in this case we're talking about with the Poisson Gamma, Poisson Lognormal, we're imagining that the over dispersion is sort of spread all across all of the sort of all the count levels here, whereas the zero inflated Poisson is very explicitly putting higher weight on the zero count case. But all the rest of the counts remain described by a standard Poisson, and that has rather different behavior than what we've seen here. Actually, what I'll do is here, let me just open it up to any last questions for today's session. As I say, what I'm going to do next time is spend a little time at the beginning of the lecture talking about the zip case. And let's see, a question here is, can zip be combined with the negative binomial? And sure, there's no reason why it couldn't. You could imagine, I could certainly imagine a case where you may combine what is just a simple sort of continuous distribution of hazard rates across a bunch of patients, for example, but then also have a very distinct subset of patients who simply aren't prone to whatever the event is that you're counting. And sure, you could do a zero inflated negative binomial. Obviously, it's a slightly more complex model, but if the data and what you know about the context warrant it, sure, there'd be no reason why you couldn't. I'd actually have to think about implementing it in. Actually, I think you could. Actually, probably wouldn't be hard to implement. I think I could implement it pretty straight ahead. Maybe I'll actually think about doing that for Monday. The question is, have people used the combination often? The essentially the zip with the negative binomial. I'll just have to say I don't know. I haven't seen it used often. I've generally seen zip talked about on its own, but I don't want to pretend that I know the broad statistical literature on it well enough to really make a clear statement on that. Okay. By the way, I should mention too that here I've been using WinBUGS all the way through. These models can also if you want to do them in a more conventional context, especially when you're not dealing with longitudinal data where you need a mixed effects model, you can do sort of standard frequentist approaches using GLM inside R, though it can be a bit more awkward to implement some of the more complex ones. Doing the plain Poisson is real easy. Doing the negative binomial is a little bit harder, only because it's I find the parameterization that's used in GLM a little less flexible, but it can certainly be done there. If you need more flexibility, then you have to entertain things like using elements that come out of things like NLME that allow for some of these elements, but you can do it. In fact, I've sometimes done that to get initial estimates for some of these. Okay, well, if no more questions, I'm going to go ahead and sign off. I'll go ahead and do that zip model at the start of class on Monday. If I can scratch out a little time and remember, maybe I'll go ahead and show you an illustration, I guess, of a, I don't know, what would we call it, a ZINB, I don't know, a zero inflated negative binomial. That I think that would be, I'll double check, but I think that's going to be pretty straight ahead to extend the negative binomial to include that. Okay, well, till Monday then.